think I don't have to say much about the Hubble constant and its importance for our understanding of the universe and of cosmology and so on. Measuring the Hubble constant actually has been a task for quite a long time now, basically over almost a century. It was in 1929 when Edwin Hubble realized that distant galaxies move away from us, and the more distant they are, faster they move away. And so the conclusion was, also with help of the theoretical works by Georges Lemaitre, that the universe is expanding. And these are actually the first measurements of the cosmic expansion. Plotted here is the recession velocity. It should be kilometers per second of kilometers versus distance, done by Edwin Hubble. And if you look at it, he got a Hubble constant at that time of 500 kilometers per second. And well, over the past 90 years, so until the 1960s, there was a clear trend in the Hubble constant, namely that it was declining with time. At least the measured value was declining with time. Then it has stabilized, and there was a period when the Hubble constant was somewhere between 50 and 100, people said. You could also say, some people can also say it was either 50 or 100 because different teams with different methods got either 50 or 100. And only relatively recently, basically with the beginning of this century, and the Hubble Key project to measure the Hubble constant, things got much more precise. And if we zoom into these past 20 years, this is the Hubble Key project. Then there is, with WMAP, the first CMB-based, so early universe measurement of the Hubble constant. At that time, everything still agreed around 71, 72. And then both types of measurements, so the measurements that are based on local quantities, the local distance ladder, and measurements that are based on the CMB and early universe physics, both became much more precise with time. And at some point, especially with the first data from the Planck satellite, they started to diverge. And by now, there is a relatively severe tension between local measurements and early universe measurements. You can see here there are a lot of measurements by now with different methods. And local measurements typically give values around 72 to 74, whereas CMB-based measurements give something around 67, 68. And yeah, there are like these two groups pulling about who is right and who is wrong, or maybe both are right, and it's just new physics that we don't know yet that explains this discrepancy.
I remember that in the 1980s, that there was a controversy. People would say, the solution is in the middle, 75. So now the solution is in the middle, 70.
Maybe. I mean, it's clear. I mean, there are two possibilities. Either the measurements and their error bars are reliable, then it would mean that we need something new from the theory side. Or one or both of the teams or groups have just underestimated their systematic uncertainty. I mean, that's basically the two possibilities. And well, often you say too many cooks spoil the soup, but here it's maybe not true, because what we really need is like additional independent measurements, because a lot of the, let's say, local measurements in one way or another build on a distance ladder that you have basically several calibration steps involved, and some of them are the same between different teams and different methods. So what we really need is something independent. Yeah, so here the main players is of course SHOES. That's a local measurement that's based on a distance ladder with basically a geometric calibration parallaxes, then Cepheids, and then type 1a supernovae. Then also a local measurement are megamasers. That's independent. That's a one-step measurement that doesn't require calibration and distance ladder. The same is true for lensed quasars. Holy Cow project, which I will very briefly talk later when I come to the lensed supernovae. And then, of course, there is the early universe, CMB-based studies, Planck team, and so on. And well, now, ideally, if you wanted to design an ideal measurement of the Hubble constant, you would think of these three criteria: precision, cosmological model independence, and that it's ideally an absolute distance so that it doesn't require a series of calibration steps. Precision, ideally you want competitive precision of at the 2 or 3% level. Cosmological model independence means you shouldn't go to very high redshifts. So if you stay below redshift of whatever, 0.1, 0.2, the differences between different cosmological models are basically completely negligible. And for the absolute distances, I mean, as I alluded to a few times already, I mean, if you have a one-step measurement where you have a physical model that gives you the distance of an object, that would be ideal. Whereas what's often applied in the local measurements is the distance ladder, where you have a first step, for example, parallaxes that's based on a physical model or simple geometrical model here. With that, you calibrate another rung of the ladder, like the Cepheids, and then with the Cepheids, you calibrate another rung of the ladder, which would then be the Type 1a supernovae. And every calibration step can involve some potential problems, and errors are propagated through the ladder. So if we quickly look at that, choose as one of the most precise local measurements. Definitely precise enough. It's also in a redshift range where you can say it's mostly cosmology independent, but it's based on a distance ladder, so it's not an absolute distance. The masers are one-step measurements, so they are absolute distances. They are also nearby measurements, so they're cosmological model independent, but they are not precise enough. And the main limitation there is just the number of systems that we have. And this number will not grow because there are just not enough nearby masers, and more distant masers cannot be measured properly. Lensing, strongly lensed quasars are absolute, are also precise enough, but typically lensed quasars are at redshift around 1 or 1.5, so they don't really fulfill this local requirement. So if we wanted an ideal solution, a method that fulfills it all, an ad hoc solution for all that, you can go to ad hoc, which stands for accurate determination of H0 from, no, not from crazy cosmologists, from core collapse supernovae. And so this is the ad hoc team that's in the garden of MPA in Garching.
So supernova type 2.
It's supernova type 2, yes. So the collaboration is mostly based around Garching. Some people are missing here. So this is Jason Spiromilio is behind the camera here, taking the picture. And Stefan Blondin is also not on the picture, and Sabrina Cassira. So these are basically all the people who are now or were previously based in Garching, and we have a few external collaborators as well. And we also have a web page. So why do we use type 2 supernovae? I mean, what is normally, what everybody knows what is used for cosmology is type 1a supernovae, right? And that's the usual picture that you know. You have the distance ladder for geometry, like parallaxes, and with that you calibrate the Cepheids. Cepheid distances and the Cepheid calibrate type 1a supernovae. And the reason that we have to calibrate the type 1a supernovae is that they are excellent relative distance indicators. So we can make use of this luminosity light curve width relation to standardize them. So they can be used for relative distances, but not for absolute distances, because we don't understand them well enough from a physical model point of view that we can really determine or know their absolute luminosity. So we have to anchor them, we have to calibrate them, in this case with the Cepheids. If we go to type 2 supernovae instead, they have much easier, much more simple radiative transfer physics. They're simpler systems. And that means that we can make a physics-based model from which we can directly retrieve an absolute luminosity. And so we can do a one-step distance measurement with them. So we get rid of all these lower rungs of the distance ladder and just left with the type 2 supernovae and the Hubble diagram where we can plot the distance modulus, redshift versus distance modulus. Yeah, so type 2 supernovae, explosions of massive dwarfs, massive stars. So this was previously a picture of Antares. So Antares is a massive star that will someday undergo core collapse and explode as a type 2 supernova. So we know that the progenitors are red supergiants, at least in several cases, or in all cases where we know the progenitor, it has been a red supergiant. This is an example. This is a pre-explosion image of the surroundings of the progenitor star. Then there's an image of the supernova itself. And this is a post-explosion image taken a few years later. You really see that this little red dot has disappeared. They're luminous. They're not as luminous as type 1a supernovae, but still luminous enough that you can quite easily observe them out to redshift of something like 0.3, 0.4. And by volume, they're the most common type of supernova. So they are more common in volume-limited surveys than type 1a's. Of course, if you go to magnitude-limited surveys, then type 1a's become more frequent because you can observe them at larger distances. And when we now come to the emission and the spectrum formation in type 2 supernovae, I mean, these are hydrogen-rich stars. I mean, the red supergiants that explode have retained most of the hydrogen envelope. And so the outer region of the ejecta is basically just the former envelope of the star. So it's a hydrogen shell. And within this hydrogen shell, a photosphere forms. And there is shock deposited energy behind the photosphere that diffuses outwards and is basically then released at the location of the photosphere. And the photosphere in a type 2 supernova is relatively sharp because it coincides with the recombination front that goes through the hydrogen envelope. So immediately after the explosion, the envelope is basically completely ionized, complete plasma. And then it starts recombining from outside inwards. And at this recombination front, there is basically a photosphere forming. So we have a well-defined photosphere in a well-defined medium. And with time, the ejecta expand. And the photosphere recedes inwards, at least in mass coordinates. So it approaches the inner core of the explosion. And the method that we are using to measure the distances is therefore called expanding photosphere method, because the photosphere is expanding in radius, but it's receding in mass coordinates. And you'll see in a moment what that means. Because in principle, basic principle is very easy. The devil is in the details. Yeah. So you say, okay, distance, that's what we want to measure. Distance is proportional to the square root of the luminosity. If the supernova were a perfect black body, you could say, okay, Stefan Boltzmann law, the luminosity is diameter squared times temperature to the fourth power. The temperature is something that can be quite easily measured by fitting a black body function to the spectral continuum or to the photometry that we have. So you just measure the color of the supernova and derive the temperature, basically. And the diameter of the photosphere can be again expressed as the velocity with which the photosphere expands times the time that has elapsed since the moment of explosion, right? And that's basically the ingredients that we have. So this is a typical early type 2 supernova spectrum. You see it has a blue continuum and some lines, mostly hydrogen lines on top. So you can fit a black body, you can derive a temperature. You can take a look at the lines. These lines have characteristic shapes that are called Picigny profiles. So they are Doppler broadened and they have an emission and an absorption component. And this is characteristic of lines forming in expanding media and winds or whatever. And the usual thing is when you have such a Picigny profile, absorption, the position of the blue shifted absorption is basically characteristic of the photospheric velocity. It can also be a little bit larger than the photospheric velocity, but this is roughly a measurement for the photospheric velocity. And if you then, for example, also have a good light curve, like this is an exceptional light curve because this was taken by the Kepler satellite. Normally we don't have anything like this, but if you had it, and you would know the time of explosion very well, then you basically have all the ingredients that you need to calculate your luminosity. Well, in reality, it's not that easy, as usual, because the supernova is not a black body, of course, and has lines, as we saw already. We also need the lines because only with the lines we can measure the velocity. But what is even more important is that the actual flux of the supernova is only a fraction of the corresponding black body flux. The true supernova flux, something like this, it's strongly diluted. And we need to know this dilution factor very precisely because otherwise the whole method is pointless. And these dilution factors have been computed in the early times, meaning like in the 1990s. One has done some radiative transfer simulations for a standard type 2 supernova and derived such a dilution factor, and that has then been applied to all supernovae type 2 when doing EPM, but not all type 2 supernovae are the same, so that was very... It's 15% of the flux of a black body at that temperature and with that photospheric size. Yes. Yeah. I mean, for it to be a black body, it would have to be, you know, equilibrium, etc., 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 and it is not in equilibrium at that stage. So in reality, it's really strongly diluted. So to really come into a regime where you can say you can precisely measure distances and precisely determine these dilution factors, you really have to individually model each supernova basically that you're looking at. And this has been done, starting in the 1990s and then in the 2000s was then called spectral energy, spectral fitting expanding atmosphere method or tailored expanding photosphere method. This is roughly the same thing. You set up a configuration like your hydrogen envelope with a certain composition, with a certain density profile. Your optimizing these parameters that you have to match the spectrum as well as possible. And then from that model, you basically derive a luminosity. Problem is that this is very complicated and very time consuming. I mean, the radiative transfer calculations take a long time, and then you have to optimize the structure in an iterative process and so on. And so in total, in the literature, when you look in the literature nowadays, this has been done for 3 type 2 supernovae as more proof of principle. And all of them were nearby objects with very good data sets where you could play this game. So none of them are in the Hubble flow. So nothing of that can be used for cosmology at the moment. And we want to do exactly that. We want to apply this method to cosmological sample for cosmology in the Hubble flow. The radiative transfer code that we use is TARDIS, which was developed by both Katzendorf and Stuart Sim. It assumes an inner boundary that can be pretty deep inside the ejecta if you want. Then you have your atmosphere layers with adjustable composition. At the lower boundary, you're injecting energy packets in a Monte Carlo sense. So you're following the Monte Carlo packets through the envelope, go through all the processes. And then when they are released, they are counted towards the spectrum, and you basically get your spectrum. Initially, this code was written mostly for type 1a supernovae. So to apply it to type 2 supernovae, it had to be improved, and changed a little bit. So additional processes had to be taken into account, especially continuum processes, bound-free, free-free, collisional processes that are not so important in type 1a supernovae, that are, where the ejecta are much more metal-rich, and so they are really line-dominated. Here, type 2s are more continuum-dominated. NLTE for certain species had to be implemented, and several other smaller things. So this is all work, these improvements done by Christian Vogel in our group in Garching. And I would say, if you ask me, he is the key person for ad hoc, because he is really the person who is doing and developing all the modeling. So without him, we would have no chance ever to play this game. So does it work? Well, I would say at least it reproduces the observed spectra pretty well. As you can see here, for one supernova that has also been studied already several times in the literature, we see spectra at different times from explosion. And I mean, there are small differences here and there, but all in all, I would say the match is compatible or comparable to the best other spectral fits for supernovae you find somewhere in the literature. So we have an observed spectrum. How do we derive the parameters? Well, the traditional method, as I said, is you try to do the radiative transfer fitting basically with an optimization by hand and eye, so that you start with a certain set of parameters, you get a spectrum, you say, this doesn't look quite right here and there, and you have a feeling which knobs you have to turn to improve the fit. And you do this iteratively several times, and then from the strength of the line, basically you can get an estimate of the metallicity of the composition. From the position of the line, you get the photospheric velocity. From the whole continuum, that's basically the temperature, and putting all this together, you get luminosity. The advantage is that if an experienced person is doing that, you can arrive at very good fits, actually, because the person has the understanding which knobs to turn to arrive at a good fit. But the disadvantage is that it's very time consuming. It's impossible to do this for a large amount of data. And it's also in the end a subjective measurement. It's not reproducible. If you put another person there, the other person will arrive at a slightly different solution. And you have basically no handle on uncertainties. And as we all know, when we want to measure a quantity like the Hubble constant, in getting a value of whatever 72 is nice, but without an error bar, it's worthless. Yeah? So to overcome this problem and the problem of the huge amount of time that this needs, what we do is spectral emulation rather than spectral simulation. So these emulation techniques have been discussed in the literature in the past, also by a student from MPA. And the idea is basically you have a pre-computed grid that's really simulated, and then you just interpolate on that grid. And the big advantage is that a simulation takes something like 1 day per simulated spectrum with all the physical processes that you have to take into account. Whereas the emulation takes fractions of a second. It's a speed up by factor 10 million or so. The reasoning behind it, that it works, is that, well, there is no reason to assume that the spectra don't vary smoothly when you change parameters. I mean, nature typically behaves in a smooth way. It doesn't mean that it has to behave linearly, but at least smoothly. And in fact, Christian has shown in a paper that the errors that you make with emulation versus full simulation are almost, in almost all circumstances, below 1% per spectral bit. So that's very little and will never become a relevant or dominant error term when thinking about the error bar on the Hubble constant. And with this very fast method, you can then basically use classical optimization algorithms and do whatever chi-square optimization, get the best fitting spectrum and the best fitting parameters, along with probability regions and error bars and everything. We have already tested, this is not yet published, but we have already tested this for a number of supernovae from the literature that are, let's say, in the nearby Hubble flow, type 2 supernovae that have fairly good data sets, fairly good estimates of the time of explosion. There are only 6 mentioned here, and we had trouble finding these 6, actually. I mean, it's there are not that many that are useful.
How many spectra do you need for this to work?
It depends a little bit on how good the time of explosion estimate is. If you have a very good time of explosion estimate, then in principle 1 spectrum is enough. Otherwise, you need a series of spectra. Yeah, so here's an example. You start from the supernova, you model different epochs, different spectral epochs. Also the reddening, the foreground reddening has to be determined within the fit process. And then you end up with probability contours on your parameters. And so this is the result for these few literature supernovae. I mean, the individual supernovae gave Hubble constant somewhere between 67 and 78. If you combine them, you arrive somewhere at 72, plus minus. But this is still preliminary, yeah. So the study will be published relatively soon with a few more supernovae inside. So don't take these values as don't cite these values at the moment. Yeah. So for the ad hoc project, for the actual ad hoc project, this is not just about the improved modeling and the theory side, it's also a project on the data side. And so from the data side, I mean, starting from the precision that you want on the Hubble constant of something like 2 or 3%, then you say, okay, we can maybe get individual supernovae to something like 10%. So you need a number of objects to reduce the statistical error. To get it to 2%, you would need something like 20, 25 objects. These objects should be in the nearby Hubble flow. Because, I mean, this is basically the precision for the distance of the objects. Here, we are talking about the redshift uncertainty, so the other axis in the Hubble diagram. And if you go to very nearby objects, it's clear galaxies have peculiar velocities and you have peculiar flow patterns in the local universe and so on and so forth. And if you go to a redshift of 0.01, a characteristic typical peculiar velocity of a galaxy of 400 kilometers per second can result in a 13% uncertainty. And this reduces to 3.3% if you go to 0.04. So you definitely want to go to a non-negligible redshift, ideally something like between 0.05 and 0.1. And so that was your question about the number of spectra. So with one spectrum, the uncertainties are relatively big. By having several spectra, one can reduce the uncertainty, of course. So what we aim for is several spectra taken within the first month of explosion, basically. Because that's also the phase where the method of the radiative transfer modeling works best. And spectra have to be well calibrated, and ideally you have just one instrument so that you don't have the problem that you have to sufficiently well characterize a lot of different instruments. And in the literature, such data don't exist. And that's why we took the data ourselves. So we wanted something like about 20 supernovae in that redshift range, 0.04 or larger. And that's doable, definitely, but you need fairly big telescopes for that, because a typical type 2 supernova that has a magnitude of, absolute magnitude of -17. If you go to 0.04, it has 19th magnitude, apparent magnitude, and if you go to 0.08, it's already a 21st magnitude, and that means you have to go to 8 or 10 meter class telescopes. We want spectra, we want photometry so that we can get the colors and calibrate the spectra very well. We decided that the VLT and the force instrument are like the best choice to get all this, and we applied for a large program at ESO and got it. So we were awarded 150 hours spread over 1.5 years. And the whole project started in October 2019 and started very successfully. We observed several supernovae. Then, as we all know, this nasty little virus came and the telescope were not working for half a year. So the whole thing was delayed. We resumed the observations in October 2020, and they were ongoing until October 2021. And now, at the moment, we're still taking some template final reference images for the photometry so that we can apply template subtraction, get rid of the galaxy, get more accurate photometry. But in principle, you can say the data are taken. And that's the typical data set that we have. So that's 6 spectra taken between maybe a week after explosion and something like 30 days after explosion. You see the evolution, and this is a series that will be fitted. We also got with the 20 or 21 supernovae that we observed in the end, we have fairly good distribution on the sky, which is important because at least at the low redshift end, we are still not completely independent of local flow patterns, and having a good distribution helps to fight systematic uncertainties coming from there. That's the redshift distribution of objects that we got. It peaks pretty much at the low end of what we were aiming for, and that's simply that we were limited by the surveys, the supernova search surveys that don't go deep enough to, most of them don't go deep enough to find objects of 21st magnitude. So a lot of the supernovae we found were around magnitude 19, 19.5, and that means redshift 0.04, 0.05. But that should still be good enough to be, yeah, relatively safe that we are not dominated too much by peculiar velocities. Yeah, of course, also here there are some skeletons in the closet. The systematics, nasty systematics. I mean, there are definitely systematics related to the radiative transfer treatment. I mean, that comes with some approximations, etc. I mean, nothing is perfect. We're trying to characterize this by comparing the TARDIS code to another radiative transfer code, CMF-Gen, to see how well the two agree. I mean, there is no absolute test, but at least you can do this differential test between two codes. There's always the problem that there might be circumstellar material around the supernova. Yeah? The progenitor system might have lost some mass prior to explosion. And when the supernova ejecta run into the circumstellar material, some of the, we have shocks, things are heated up, kinetic energy is transformed into luminosity with a certain efficiency. All of that is not really treated in the radiative transfer. And if there is a significant contribution from CSM interaction, would definitely be a systematic problem in the method. We may have to deal with peculiar extinction, meaning, I mean, we are fitting for the color excess, but if we have to deal with non-standard dust with R sub B values that are different from the canonical 3.1, becomes difficult because, I mean, of course, you can also include the R sub B as an additional parameter in fitting, but at some point you have so many parameters that, yeah, it's hard to really constrain them. There may also be effects that the expansion is not homologous, that this easy, simple expansion that the radius is basically the velocity times time does not hold for various reasons. Also, that gives you a deviation, possibly systematic deviation. And there are certainly more effects that may play a role. And I mean, that's the stage we are in now, basically, that we are thinking very heavily about the systematics, so that in the eventual H0 publication that will hopefully come at some point, we have a really thorough study of all the systematics. So the summary for the ad hoc project is it's a distance ladder independent measurement of the Hubble constant with the type 2 supernovae. Based on literature data, we have a proof of principle demonstration where we got a Hubble constant of 72. We have a dedicated data set on which we can finally play the game. And yeah, what is to be done now is the final data reduction, testing, systematics analysis, and so on. So since I promised two methods and since it's already late, the second one will be much briefer. That's definitely a thing we want to do. So one idea is also we want to observe, also now with future programs, want to observe type 2 supernovae that explode in galaxies where there are type 1a supernovae. So you can then, for example, use type 2 supernovae to calibrate the type 1As and replace basically the Cepheid distance ladder with type 2 calibration. Or you can look at galaxies where you have a type 2 supernova and you have Cepheids. I mean, all these are tests and stuff we are doing. But of course, they should only be used as a test because in principle, I mean, we want to do our own one-step measurement. I mean, we should not say, okay, but the Cepheids tell you a different distance for that galaxy, so we have to
no, you have to ensure that you are right.
Yeah.
And test the line.
I mean, it's also the main analysis here with ad hoc is blinded. So we will at some point, when we are basically confident that we have taken all the effects that we can take into account, that we have taken them into account, then we will unblind and we will not change the value of the Hubble constant that we get out anymore. Yeah. The second technique is with lensed supernovae. The program is called HOLISMOKES. And yeah, what do you have to imagine when we talk about HOLISMOKES? Yeah. Well, it's of course, it's again an acronym. And if you found the ad hoc acronym already strange, then you will beat me for that. Highly optimized lensing investigations of supernovae, microlensing objects, and kinematics of ellipticals and spirals. Isn't that beautiful? So it's about strongly lensed supernovae, strong gravitational lensing. It's something that happens when you have a distant background object and you have a foreground galaxy that's between the observer and the distant background object. And the gravitational potential of that galaxy bends the light. And in the strong lensing regime, you get actually multiple, typically 2 or 4 images of the background object. And the different light rays have different path lengths, and they suffer from different gravitational time delay in the lens galaxy. And that means that the light on the different rays for the different images arrives at the observer at different times. Normally, you don't notice this unless your background object is variable, is a transient. And that's why for measuring the time delays, you need something like a quasar, as is shown here, or a supernova. And the time delays are important because with the time delays that you can measure, you can basically calculate a quantity that's called the time delay distance. That's a method that was proposed already in the 1960s, 1964 by Refstal. So what you need is the measured time delay. You need the Fermat potential of the lens that comes from lens mass modeling. With these quantities, you can derive the time delay distance, and the time delay distance is proportional to 1 over h0. So that's the principle of the measurement. And funnily enough, Refstal in 1964 envisaged this method already and discussed it for lensed supernovae. But it was then actually applied to lensed quasars first. That's the Holy Cow project that I already mentioned at the beginning. There are now several lensed quasars for which people have played this game. And this is not the very latest version of it, but in principle, nothing has really changed. I mean, you get individual distributions, probability distributions for the Hubble constant from different lensed quasar systems. You can combine them and get something like 72, 73, in agreement with other local determinations of the Hubble constant, and in disagreement with the early universe measurements from the CMB. Yeah.
What is the therapy? For instance, what is the time delay that is
for the lens quasars, you mean?
Yeah.
the typical time delays, I mean, the time delays can have a relatively wide range.
Yes.
Basically, depending on configuration of the system and so on, it can range between hours and years. Yeah. Especially if you have not a single galaxy as a lens, but a galaxy cluster, then the time delays are often very long.
Yeah, so I think the question could be, how can you get that this supernova is not a new object, and this is a lens, this is the same one?
I mean, there are different things. I mean, first of all, when you see a supernova exploding in something like this, would probably
Wait for the lens.
Guess that this is a lens, and you can even predict by doing some lens mass modeling when and where the next image will appear. There is also another hint that an object, that a supernova can be lensed. That's the magnification, right? You have a magnification factor, and that means that the supernova does not have the magnitude that it would normally have at the given redshift. Also, the redshift of the supernova doesn't match the redshift of the lens galaxy, but it's far behind. But these are all things that you can use. So strongly lensed supernovae versus strongly lensed quasars have several advantages. One advantage is supernova fades away after a year or two. That means you can afterwards see the system without the supernova, see the arcs from the supernova host galaxy and so on, and get spatially extended information that can help you to do accurate lens mass modeling. Whereas the quasar will always be there and outshine its host galaxy. And that makes the mass modeling much less accurate, let's say. So that's the one thing. Second thing is just the characteristics of the light curves. I mean, here, these are quasar light curves, with erratic variability. These are the 4 images of a lensed quasar. And I mean, you see the time delays are here probably something like maybe weeks or something like that. The problem is, because of the relatively low amplitude and the erratic nature of these light curves, you have to monitor them over very, very long time scales. So typical lens quasar monitoring goes over 10 years or more. Because there is an additional complication, namely that you have microlensing distortions on light curves. So the individual images can also be additionally lensed by individual stars or individual compact objects in the lens galaxy. And that distorts the light curves. With such erratic light curves, you need a long temporal baseline to really get a good time delay. Supernovae have much easier light curves. Yeah, typically if it's a type 1a supernova, you have a smooth rise, you have a smooth peak, and then a smooth decline. And so getting a time delay by matching them is much, much easier, even if there is some microlensing distortion. And so that's why the HOLISMOKES team wants to measure lens supernovae. That's our team, again, mostly based in Garching. The I is Sherry Suyu. There are also some friends from other institutes, but I would say most of the activity is in Garching. And so now I talked about the advantages of lensed supernovae versus lensed quasar. The disadvantages, the main disadvantage is that they are extremely rare and hard to find. Because they are rare and they are typically very faint. And actually it took something like 50 years after the prediction by Refstal, or the description of the method, that the first lensed supernova was actually found, which is nowadays called supernova Refstal. And that was a lensed supernova discovered in Hubble Space Telescope images by chance. That was a nice case when there was then lens mass modeling, which was pretty complicated because the lens was a galaxy cluster in that case, a complicated mass distribution. And there was a prediction that there will be another image several years later in a certain location. Different groups had different predictions. It really showed up then. And from that, one could make a first time delay measurement and first estimate of the Hubble constant. But of course, it's an uncertain mass model. It's just one object, so the error bar is pretty big on that. What we want to do instead is we don't want to wait for like chance detections in Hubble Space Telescope images. What we want to do is we want to search for lensed supernovae in a systematic way. And we want to do it by searching for transients that happen in known lenses. And for that to be efficient, one needs to increase the number of known lens systems. And so one part of the project is to search for new lenses. And we're using convolutional neural networks to that. I mean, convolutional neural networks plus in the end some, by eye screening of the remaining systems. And then we have by now big catalogs of several thousand lensed or possible probable lensed systems. And then we are looking into sky surveys, and whenever there is a transient in one of these systems, we take a closer look. And at the moment, we are mostly making use of the Zwicky Transient Facility as a feeder survey. CDF is on a small telescope and has a camera with an enormous field of view, 47 square degrees. This is the size of the full moon camera. But since it's a small telescope, the survey is not particularly deep, so the limiting magnitude, upper magnitude is about 20.5. And predictions say that 99-point-something% of all lensed supernovae are fainted in that. That's, I mean, at the moment, we have just a chance to find the tip of the iceberg. But things will change drastically in a year or two when LSST, the legacy survey of space and time, will start, which is a dedicated 6.5-meter telescope in a perfect location in Chile. Camera is not quite as big, but goes much, much deeper. So with limiting magnitude in single images close to 24. And with that, predictions are that we will find a lensed supernova like at least one per month or so.
Sorry. So as for the DDF, for instance, do you flag the objects, or you check every day the candidates, or how do you do it?
We check every day the candidates from CTF, cross-match them with our list of potential lenses, and whenever there is a match, we look at the object, look at its history. I mean, most of the objects that we find are lensed quasars.
Yeah. So you don't,
because they also show up in CTF.
So you just don't take the ones that were crucified as supernovae, you take all the candidates.
Yeah.
They're not all.
Yeah. Yeah. I mean, it's still not a huge number of matches, and most of the matches, as I said, is with known quasars. Yeah. So at the moment, we are still waiting for the first suitable lensed supernova that we can play all this with. But we are, of course, not sitting around and just waiting, and we are doing some preparatory works and also have already some papers published. So HOLISMOKES 1, first paper of the series, it's basically project overview and some simulation, some estimation of the accuracy, of the precision on H0 that we can achieve with that. Then there is a series of 3 papers around lens search so that we can increase our lens catalogs that we can cross-match the new transients with. All of this is based on convolutional neural networks. This is a compilation of some of the lenses that we found in the HSC footprint with this method. And there are some works that deal with measuring the time delays, getting rid of the problems that are introduced by microlensing, et cetera, using photometric methods, spectroscopic time delay measurements, because, I mean, as we saw before, from the Picigny lines, right, you have blue shifted absorption that gives you something like a photospheric velocity that evolves with time. So basically, if you make a measurement of the position of an absorption line, you can also use this as a clock, as a timing, and from that measure time delays rather than from light curves. And finally, there is a set of studies around improving lens mass modeling or making it more efficient, also with the help of neural networks. Because in the end, I mean, full traditional lens mass modeling takes a while. And if we find the first image of a probably lensed supernova, we want to be able to predict like an upcoming image and time delay relatively quickly so that we can point our telescopes there at the right time so that we don't miss it. So we need something to get a rough prediction of time delays within a day or something like that. And that's where these works are for. And yeah, status is principle, as has already been shown by the lensed quasars, also lensed supernovae can provide direct distance ladder independent measurement of the Hubble constant. We are currently monitoring CTF. We will probably more successfully monitor the LSST stream of transients in the future, and then hopefully also find some lensed supernovae. We are preparing for this, and we're eagerly waiting for our first lensed supernova. Yeah, that's it. Thanks a lot for your attention.
Any questions? Can you simulate current emulate slide? It seemed to me that there were some features in the black curve that weren't matched at all by the blue curve. Why is that? Or maybe I just misread it, but why is that?
That's right, but it doesn't have to do with simulate versus emulate, because the black curve was the observed spectrum.
Right.
So that's more the question of how well can the radiative transfer code reproduce the observed spectrum. And I mean, as I said, I mean, the radiative transfer treatment is not perfect. You're making some assumptions here that are not perfectly fulfilled in reality. Like, for example, you assume that above your lower boundary, you have a density profile that's characterized by a power law with a fixed power law slope. In reality, this can be some much more complicated profile. And so these are limitations that make it impossible to really reproduce all the details, all the fine features perfectly.
There's just one, the big one that's missing.
Yeah, this one.
Yeah, exactly.
It can also have to do with atomic data, you know. I mean, all the radiative transfer calculations can only be as good as the atomic data that you feed into the code. And there are actually still a lot of shortcomings when it comes to atomic data, to collision strengths, and so on and so forth. There's also relatively little progress in that field, because calculating atomic data, cross sections, and so on for a large number of ions is not the most rewarding thing to do. So that's not really sexy, and I mean, we rely on that, but nobody wants to do it, right? That's the problem. So there are many reasons for many possible reasons why such a deviation can show up. And the hope is always that this will not result in a big systematic error when propagated through to your luminosity and to your distance.
Regarding the emulate as well, I see that in the HOLISMOKES you use a lot of machine learning and stuff. For the emulate, you do normal fitting, right? But I think there's also interesting applications for emulation.
You're interested in the emulator, I can show you one more backup slide if the computer lets me do it. I mean, I'm not the expert about this emulator stuff, I have to say. So it's as you see, I mean, there is PCA involved, dimensionality reduction, Gaussian process regression.
Okay. Oh, I thought it was just a fit to the interpolated spectrum.
And here, that's a direct comparison basically between emulated and simulated spectra. That's basically the fractional difference between emulated and the simulated spectra. And here both are plotted on top of each other. And I mean, without zooming in, you would not see a difference at all. And that's for 3 different epochs. I would say this is most likely not the biggest source of uncertainty that we have. But it helps enormously to be able to do this whole fitting process in an automated and objective, quantitative way, including errors and everything. Any questions?
So you said this is not the main source with respect to possible error systematic. So what is your main concern? Is the CSM?
CSM is definitely a concern, yes. I mean, there are studies by Hillier and Dessart who have tried to figure out how type 2 supernova spectra are modified when there is different amount of CSM around the supernova. And it's clear, I mean, at some point, if there is an enormous amount of CSM, you get a type 2N supernova, and you would recognize it immediately, and you would not try to use that. But there is not black and white. I mean, there is a lot of gray shades, and some signatures that you have from CSM are actually also present in our data set in some of the objects. So we will definitely have to split our sample in, let's say, a gold and a silver or whatever sample, and see whether it makes a difference, including or not including the objects that likely have some CSM. So that's a point. Then the question is, extinction reddening is always an issue. Maybe not the most severe here, but yeah, can always play a role. And there are also some uncertainties related to the modeling. I mean, the radial transfer, for example, is, I mean, these are steady state calculations. They're not time dependent. But otherwise, you could not do all this fast fitting and so on and so forth. And in the comparison to time-dependent calculations, we see that after 20-25 days, there starts to be a deviation in the estimated luminosity. So either we disregard like the latest spectra that we have, or we try to somehow include, let's say, this main, it's mostly the time-dependent ionization. So mostly, yeah, that we try to include that in some way in the otherwise state calculations. So there are still some of these issues.
If you enjoyed the video, like and subscribe.